Alright, so this is the last video on the proofs and logic series, and we're just going to be going over some basic notes on how to actually read and write proofs. We'll be going over two examples today, and these are examples that we've dealt with before. And the first theorem is if we have two sets, A and B, then if A intersect B is equivalent to A, then A is a subset of B. So this is the first theorem, which we will write a proof of. This is an example that we've done before, and this is from part 18 or episode 18 of the video series. So if you need a refresher on that, then go ahead and watch the video again. It will help to familiarize yourself with how we approach the proof towards this theorem. So, well, what is the first step of proving a theorem? Well, if we have a statement of the form if P then Q, then, well, just follow the basic principle, right? We put this to the left side of the table and we put this to the right side of the table. The left side is what we know or what we assume to be true, and the right side is what we need to show or what we need to prove. So let's write that down. So we begin by saying, let us assume that A intersect B is equal to A. And then we're going to write, then we need to show that A is a subset of B. So this is our first sentence of the proof, and this is how most proofs start. We begin with stating what resource or what statement we are allowed to assume, and then we also state our goal, what we are trying to show. And then after that, what we do is we manipulate the left side of the table and we manipulate the right side of the table, and we keep simplifying things until there is sort of an easy connection to draw between the two sides of the table. Except now we have to write that all down. We have to document it, and we have to be detailed when doing so. I remember that on the right side of the table, we simplified things by saying, not saying, by converting this into if x is in A, then x is in B. Obviously, this is just a restatement of that. So instead of proving this, we can prove this instead because they're equivalent, just restatements of each other. And presumably, this is going to be much easier to prove, and it'll be useful to us to think of it in this way instead. So that's what we're going to write down as well. We're going to say this is the same as showing that if x is in A, then, okay, I'm not going to use arrow, I'm going to write it like in actual English, then x is in B. Okay, so we simplified the right side of the table, and this we explained how we did that. And then after this, I believe we went one step further ahead. We simplified things even further, because if you notice, this is an if P then Q statement. So this means we move this over to the left side and we keep this on the right side. So let us write that down as well. I'm going to write here. So assume x is in A. Then we need to show that x is in B. And this is the full simplification of the right side of the table. And the process of that simplification is documented down with these sentences. And I don't think there's any way to break things up even further. This is as simple as we can get. Alright, so what do we have so far? These are the things which are on the left side of the table. These are what we know, what we can assume. So just keep that in mind as we continue writing. Alright, So since we're done with the right side of the table, let's move to the left side. All right. So we know that A intersect B is equal to A, but A intersect B equals A means that A is a subset of A intersect B. Okay, so this is another piece of information that we can use. We write that down so that the readers know that we're going to be utilizing this piece of information. And we can actually break this down, simplify it even further by expressing it in terms of logic. A intersect B equals A means that A is a subset of A intersect B, which in turn means that anything inside A is inside of A intersect B. So this is actually for all x in A, x is in A intersect B. So this is just the logical statement of that, right? This is what it means to be a subset of something. This is how we write that in terms of logic, and then we're just converting logic into English because that's easier to read and to process. Alright, so what's next? Well, we have this assumption. This is on the left side of the table. So let's just use that piece of information. Since x is inside A, it is also inside A intersect B. So we're combining this piece of the puzzle and this piece of the puzzle together. And the way we do that, we explained with this sentence over here. We are still not done yet because our goal was originally this, but it converted. We reformulated the right side of the table. So then our new goal is this guy instead. X is in B. Right now what we have is X is inside A intersect B. So that's not quite there yet. I'm just gonna write it down. Our goal is X is in B, and what we have currently, what the readers currently know and understand is that X is in A intersect B. So we're not quite there yet. We just need a couple more sentences. Okay? Alright. But if X is inside A intersect B, well, what does intersection mean in terms of logic? It means that X is in A and X is in B. But then X is in B is what we needed to show, so the proof is complete. And that is how you write a proof. Alright, so this next theorem, which we will write a proof of, is this theorem over here. There exists an X which satisfies if P then Q, and this whole thing, if this whole thing is true, then it satisfies for all X, Q of X is true. This is one unit here. It implies that there exists an X for which Q of X is true. So this is the theorem. It states that if this happens, then this happens. So just this is one unit, this is one unit, just to make things clear. Okay, let's get started on how we would write the proof of this. Okay, so let's just do the same thing we did last time. So we move this to the left, we move this to the right. So let's write that down. Let us assume that there exists an X such that if p of x, then q of x, then we need to show that, well, what is this? Let's try to convert this into English because it's actually pretty difficult. This means that all x values satisfy p of x, and this means that there exists an x which satisfies q of x. So we need to show that if for all values x, p of x is satisfied, then there exists an x for which q of x is satisfied. So what's the next step here? What do we have to show? We have to show that if blah 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 blah, then blah 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 blah. And in general, whenever we have to show that a statement of the form if p then q is true, which is this thing over here, if we have to show that all of this is true, then this is the same thing as, well, placing this guy on the left and placing this guy on the right. So we just repeat the same process over again, which means we can assume more pieces of information, basically. So what are we placing on the left side of the table? Okay, we're placing this thing on the left side of the table, so we can assume more things. So let's write that down as well. So then assume that for all values x, p of x is satisfied, then we need to show what we need to show. We just have to show this thing, the thing that we placed on the right. Then we need to show that there exists an x for which q of x is satisfied. So this thing that we have underlined, it's things on the left side of the table, things that we know to be true. So these are our puzzle pieces which we're supposed to use in order to prove what we need to show. Now, what we need to show is not this statement over here. We have already converted this whole thing into the bottom statement over here, right? So our new goal is to show that there exists an x for which q of x is satisfied. Let's see what the puzzle pieces can do. So we know, I'm just going to write the top part here again. We know there exists an x, and we're going to say call it x1, such that if p of x1, then q of x1. But we know p of x is true regardless of the x value, because of the top statement which we assume to be true over here. For all values x, p of x is satisfied. So we know that p of x is true regardless of the x value. This is just a restatement, just to make things easier, just to make the thought process easier to follow. So therefore, p of x1 is true. We know that p of x1 is true. We know p of x1 is true. So q of x1 must be true. Why? Well, because if p of x1 is true, then q of x1 must be true. So since we know p of x1 is true, q of x1 must be true. Well, a lot of logic is just like restatements of each self, because a lot of things are equivalent to one another, and we have to like repeat the things that we say just to make a point that they're equivalent. So a lot of logic is just repetitive and redundant statements over and over again. And we can actually stop here. That's the end of the proof. Why? Well, we need to show that there exists an x for which q of x is satisfied, and we know that q of x1 is satisfied, so this x value, which we need to show that exists, is x1. And we know that x1 exists, just based on what we have written over here. So x1 exists, and it satisfies the q statement, so everything is fine. We have proved what we needed to show, and then the end. So these are our two proofs. And if you study them very closely, these two proofs, you'll see that there's quite a resemblance in their structure. And most proofs, when you're writing them, they follow mostly the same process. So as long as you keep practicing, then you'll get it eventually. Each proof is different to write, but at the very, very deep essence of it, it's just the same process. And once you realize that, things are going to get easy. So I hope that these two examples have been enough. It takes a lot of time, so I can't do more examples. That's it for the proof and logic series. Congratulations if you've made it this far. And that's it from me. See you.